The theme of my work is sarcasm detection in news headlines. My work aims to create a program to identify sarcasm in news headlines using machine learning techniques like logistic regression and naive bias classifier, and neural networks with Glove and Word2vec embedding weights. Then I will compare results of different methods. Newspapers often seem to employ sarcasm in their headlines to grab the reader's attention. And too many people think sarcastic news is real. However, more often than not, the readers find it difficult to detect the irony in the headlines. So they get in the wrong idea about the particular news and further passing on their understanding to their friends and colleagues. So detecting sarcasm is difficult for humans, not alone computers. Such a system that can automatically and reliably detect sarcasm is more critical now than ever. First of all, I need to find the correct data for my research. Then I need to do some pre-process of the data, like remove symbols that do not contain useful information, such as punctuation, URLs, numbers, and stop words. Then, after pre-processing, there is a need to tokenize the data. This stage is for vectorizing, like simple tokenizer or Word2vec or Glove. Then embedding features like TF-IDF, it will be for the future model. Then, after separating the data for the training and testing set, I will be ready to build and train my model. This start is a general one. So let's see the activity diagram. Here is the activity diagram of my program. At first, I read JSON file in pandas table. Then I delete stop words, numbers, punctuation, and links. So that data is ready for building vectors. Tokenize data and vectorize data with TF-IDF. What is TF-IDF? TF-IDF is a numerical statistic that represents the importance of the word. So it's typically used to stop filtering words in text, summarization, and categorization applications. So it fits for sarcasm detection. Data splits into two sets, training and testing. And then those sets are used in training of logistic regression and naive bias models. And we get a result. Result will be presented as confusion matrix and accuracy. At the same time, processed data is used for embedding weights using Glove and Word2vec methods. Using weights and tokenized data sets, it trains neural networks for sarcasm detection. This and as well, the default neural networks will be trained. Default means that one neural network will not have any weights. The following diagram better shows everything with time is sequence diagram. Here you can see that after preprocessing, the data is tokenized and vectorized. Then logistic regression model work with tokenized sets and return the results. Then the logistic regression model work with feature sets and return the result. As well as naive bias model works with the same sets and returns the result. After that, the neural network model starts with tokenized set. Then it builds weights with Glove dictionary, and the last model have weights from Word2vec vectors. And here you can see the difference in headlines before and after the pre-processing. Numbers and punctuation are gone, as well as stop words like with, my, or to. Here you can see word mine, with, and they're gone here, as well as numbers. So the first model that I built is logistic regression. Logistic regression is also used to detect sarcasm mainly because it's mathematically related to linear discriminant analysis. When data labeling takes place, a straightforward labeling method such as sarcastic with 1 and non-sarcastic with 0 is used to effectively facilitate the detection of sarcasm. Norm used in the penalization is L1, penalty equal L1, and algorithm to use in the optimization is equal linear. Because this algorithm performs with penalty L1 well. First time, I perform the model with simple tokenizer, and the accuracy is low, about 50%. I conclude that the usual tokenizer for such models is not enough, so additional vectorization is required. Then for logistic regression, I additionally apply extraction of features of TF-IDF from the sklearn library. After a new division of data into a test and training set based on TF-IDF, the result of the model has significantly improved to 74%. This heat map shows the confusion matrix for the model, first with default sets, and second with TF-IDF features. The axis Y is responsible for the value as they are, and the axis X is for the values provided by the model on the test data. So as you can see, more than 2,400 entires have been identified as non-sarcastic when they actually are sarcastic with simple tokenizer. But the situation is better when TF-IDF features. There is only 1,400 entries wrongly identified as non-sarcastic. The second model is with naive Bayes classifier. Naive Bayes classifier is commonly used to classify polarity, positive and negative, indicating whether the headline is sarcastic or not sarcastic. And again, the result with simple tokenizer are bad, about 50%. But the classifier with bigger additive smoothing parameter alpha, not 0.2 but 0.4, and TF-IDF features shows better accuracy, about 79%. This heat map shows confusion matrix for the models. With default sets, more than 3,000 entries have been identified as non-sarcastic while they are sarcastic. And second heat map is with TF-IDF features, where about 1,000 entries have been wrongly identified as non-sarcastic. This shows that extracting the correct features in the text improves the accuracy of the model. But the accuracy is still low. So for better results, I need to build a model on neural networks with the Keras library. The first model is a default one. There is a simple tokenizer and a default embedding layer of the model. Embedding layer using no weights. Length of constant input sequence equal 20 is the max length. And then there are two long short-term memory layers. The dimensionality of the output space is 128, and fraction of the units to drop equal 0.3. This slice returns the last output. Then there is one GRU layer and two dense layers with the activation function sigmoid. For compiling the model, I choose Adam algorithm because with the other one, the accuracy is lower than 50%. Here is confusion matrix for the model. Hence, 3,900 entires were identified by the model correctly as a non-sarcastic, and about 3,000 entires were correctly identified as a sarcastic. But there is more than 1,000 entires have been identified as non-sarcastic when they are sarcastic. And more than 700 entires have been identified as sarcastic when they are not. In these graphs, you can see the change in values, accuracy, and loss on the training and testing information depending on the efforts during training the model. The blue line stands for training data, when the yellow line stands for testing data. The loss on training data goes lower, while on testing data, the value increases. And the situation is opposite with the accuracy. The value increase on training data, but on testing data, the accuracy goes lower. The second model is with Glove vectorizer. So this embedding layer has weights. I download the document with the Glove dictionary, weight the words in it, and from an array of scales, and convert an array into a matrix to use it at the embedding layer. This heat map shows the confusion matrix for the performance of the model. Hence, about 4,000 entries have been identified by the model correctly as not sarcastic, and 3,000 entries were correctly identified as sarcastic. However, more than 900 entries have been identified as non-sarcastic when they are sarcastic, and about 600 entries have been identified as sarcastic when they are not. And once again, the loss on training data goes lower, while sadly on testing data during the test, the loss increase. And the situation is opposite with the accuracy. The value increase on training data during the training process, but with the testing data, it goes lower. The third model is built with Word2vec vectorizer, so it has weights too. Word2vec is a neural language processing application, and these heat maps show the confusion matrix for this model. More than 3,500 entries were identified by the model correctly as a non-sarcastic, and about 3,200 entries were correctly identified as a sarcastic. But there is more than 700 entries identified as a non-sarcastic when they are sarcastic, and about 1,000 entries have been identified as a sarcastic when they are not. And again, the loss on the training data goes lower while training, but goes higher during testing. And the accuracy of the data is way higher on training data, but during the testing it goes lower. So this shows that the model seems to be overfitting on training data, but during performing or testing data, it's not goes that well. All of the results recorded in the table, except the logistic regression and naive bias classifier that were trained without TF-IDF because the performance were quite low. The best results can be seen through the graph. The best accuracy is in the model with Glove, followed by naive bias classifier. It's quite surprising because my review of themed work showed that accuracy on naive bias classifier for sarcasm detection range between 60–70%, but the accuracy in my model is about 80%, 79%. Therefore, I can conclude that it's the extraction of TF-IDF features that improves the performance of the model. I can assume that neural networks trained on tests with TF-IDF features would also be more accurate, but unfortunately, when I was training such model, I encountered the problems of TensorFlow overload, because matrix with features is too big. And plus, during my experiments with neural network, like changing the length of constant input sequences, functions, adding and removing layers, accuracy range between 78 and 79%. So in the future, I can rise the accuracy by extracting more features. And that's all. Thanks for your attention.